Hello, everyone, and welcome back to the lecture series on natural and synthetic macromolecules. In nature, we find many substances with very high molecular masses that contribute significantly to the structure of living organisms and tissues. Some examples include starch and cellulose, which are abundant in plants, and proteins, found in both plants and animals. In 1827, Swedish chemist Jöns Jacob Berzelius introduced the term polymer to describe molecular substances of high molecular mass formed by the joining together of monomers, that is, molecules with low molecular mass. This process is referred to as polymerization, and as an example, you can see here the reaction of ethene monomers forming polyethene. For a long time, humans have processed naturally occurring polymers, such as wool, leather, silk, and natural rubber, into usable materials. Over the last century, however, chemists have learned to synthesize polymers by polymerizing compounds through controlled chemical reactions. Many of these synthetic polymers have a backbone of carbon-carbon bonds because carbon atoms have an exceptional ability to form strong, stable bonds with one another. Plastics are specific examples and can be molded into various shapes, usually by the application of heat and pressure. Furthermore, thermoplastic materials can be reshaped. For example, plastic milk containers are made from a polymer known as polyethylene, which has a high molecular mass. These containers can be melted down, and the polymer can be recycled for other uses. We also have access to thermosetting plastics, which are shaped through irreversible chemical processes and thus cannot be readily reshaped. In this lecture, our objectives are to recognize the relationship between a monomer and a polymer, understand the three stages of the addition polymerization process, and make the link between the macroscopic properties of polymers and molecular level properties, such as crystallinity and cross-linking. Polyethylene is a solid substance used to make thousands of plastic products, such as plastic bags, food containers, and laboratory equipment. To produce polyethylene, we must create a reactive center that can sequentially add to the double bond in each ethene molecule, extending the polymer chain and regenerating the reactive center for follow-up additions. Such reactions are classified as chain growth or addition polymerizations, and polyethylene is an addition polymer. In ethene polymerization, the reactive center that initiates polymerization is frequently a free radical. You might recall radicals and radical substitution reactions from the lecture describing types of organic reactions. In the case of ethene polymerization, radicals are commonly derived from a radical initiator, such as lauryl peroxide. These molecules contain a very weak oxygen-oxygen bond and readily dissociate to form two radicals upon heating or irradiation with light. Once formed, the benzoyl radical can add to the double bond of ethene to form a new carbon-centered radical. This step is called the initiation step. Note the use of fishhook arrows in this equation. They differ from traditional curly arrows, which represent the movement of two electrons. Fishhook arrows represent the movement of a single electron rather than an electron pair. The relative stabilities of alkyl radicals are as follows. Radicals centered on a tertiary carbon are more stable than radicals centered on secondary carbons, and the least stable are primary radicals. The next stage of the reaction is known as propagation. In this stage, the chain is extended by the consecutive addition of more ethene units through carbon-carbon bond-forming reactions. This process can be repeated multiple times, prolonging the hydrocarbon chain by 2 carbon subunits after each addition step. Propagation continues until 2 radical polymer chains meet and react, forming a completed polymer through a final carbon-carbon bond formation that terminates the radicals. This is known as the termination step. In the structure presented here, N and M are normally large integers, which may or may not have the same value. The reactive center in a chain growth polymerization does not have to be a radical. Depending on the monomer used, it may be an anion, a cation, or a transition metal complex. For instance, the most common process for polyethylene production is called Ziegler-Natta polymerization, named after the two scientists who developed the reaction in the 1950s. This process typically involves zirconium, titanium, or aluminum complexes as catalysts and is used in the formation of high-density polyethylene, also called hard plastic. An example of a Ziegler-Natta polymerization is shown here. These processes are quite complex and are beyond the scope of this course. Ziegler-Natta polymerization produces simple straight chains. In contrast, radical polymerization of polyethylene gives a polymer with occasional long branches, making it harder to pack the molecules together. The result is low-density polyethylene, which is used in stretchy plastic wrap. We can write the overall equation for the polymerization of ethene as follows. Here, N represents the large number of monomer molecules that react to form one large polymer molecule. The values of N can range from hundreds to many thousands. Within the polymer, a repeating unit appears along the entire chain. In this equation, the repeating unit for polyethylene is shown in brackets. Polyethylene is a very important commercial material. More than 10 billion kilograms of polyethylene are produced globally each year. This is a huge amount. It is equivalent to the weight of about 1.4 billion people and is roughly 100 times the weight of the Eiffel Tower. However, although polyethylene has a simple composition, manufacturing this polymer is not an easy task. Only after many years of research were the right conditions identified for its production. Today, many different forms of polyethylene, varying widely in physical properties, are known. Polymers with other chemical compositions provide an even greater variety of physical and chemical properties. In this table, you can see several other common polymers obtained by addition polymerization. The names of polymers are simply derived from the monomers used. For example, poly, vinyl chloride, is made from vinyl chloride. Polymethyl methacrylate is made from methyl methacrylate, and polystyrene is made from styrene. In 1938, a scientist at DuPont named Roy Plunkett made a rather curious observation. A tank of gaseous tetrafluoroethene that was supposed to be full seemed to contain no gas. Rather than discard the tank, Plunkett decided to cut it open. He found that the inside of the tank was coated with a waxy white substance that was remarkably unreactive, even toward the most corrosive reagents. That compound was formed by the addition polymerization of tetrafluoroethene. As it turned out, the properties of this material, called Teflon, were ideal for an immediate and important application, the development of the first atomic bomb. Uranium hexafluoride, which was used to separate radioactive uranium-235 by gaseous diffusion, is an extremely corrosive material. Teflon was applied as a gasket material in the separation of uranium-235. Today, Teflon is used in a variety of applications, from nonstick cookware to spacesuits. Plunkett's desire to learn more about something that didn't seem right is a wonderful example of how natural scientific curiosity can lead to remarkable discoveries. To sum it up, in this lecture, you were introduced to synthetic polymers produced by addition polymerization. You now know that polymers are molecules of high molecular mass formed by joining together large numbers of smaller molecules, called monomers. In a chain growth or addition polymerization reaction, the molecules form new linkages by opening double bonds. We studied polyethylene and briefly went through the 3 stages of polymerization, commonly called initiation, propagation, and termination. In the following lecture, we will examine the physical properties of some addition polymers and see how they relate to the structure of the polymer. Thank you for your attention. Hello, everyone, and welcome back to the lecture series on natural and synthetic macromolecules. In the previous lecture, you learned about addition polymerization. We discussed some important addition polymers widely used in industry and in our daily lives. In this lecture, we will try to understand the relationship between the physical properties and structure of addition polymers. The simple structural formulas you've seen for polyethylene and other related polymers can be deceptive. Since each carbon atom in polyethylene is surrounded by 4 bonds, the atoms are arranged in a tetrahedral fashion, meaning the chain is not as straight as we sometimes depict it. Furthermore, the atoms are relatively free to rotate around the carbon-carbon single bonds. Thus, rather than being straight and rigid, the chains of an addition polymer are very flexible and readily fold. The flexibility of the molecular chains can cause the polymer material itself to be very flexible. Both synthetic and naturally occurring polymers commonly consist of a collection of macromolecules with different molecular weights. You saw this when we were discussing globular proteins and their quaternary structure. In the case of synthetic addition polymers, depending on the formation conditions, the molecular weights may be distributed over a wide range or closely clustered around an average value. In part, because of this distribution in molecular weights, synthetic polymers are largely amorphous materials. Rather than exhibiting a well-defined crystalline phase with a sharp melting point, they soften over a range of temperatures. However, they may possess short-range order in some regions of the solid, with chains lined up in regular arrays, as highlighted in this figure. The extent of such ordering is indicated by the degree of crystallinity of the polymer. The crystallinity of a polymer can be enhanced by mechanical stretching, which aligns the polymer chains as the molten polymer is drawn out. In such cases, the intermolecular forces between the polymer chains hold them together in the ordered crystalline regions, making the polymer denser, harder, less soluble, and more resistant to heat. For instance, the data in this table shows how the properties of polyethylene change as the degree of crystallinity increases. The simple linear structure of polyethylene supports the intermolecular interactions that lead to crystallinity. However, the degree of crystallinity in polyethylene strongly depends on the average molecular mass. Polymerization results in a mixture of macromolecules with varying values of N and, consequently, varying molecular masses. So-called low-density polyethylene, used in forming films and sheets, has an average molecular mass in the range of 10,000 unified atomic mass units and exhibits substantial chain branching. In other words, side chains extend from the main polymer chain, much like spur lines branching off a main railway line. These branches inhibit the formation of crystalline regions, reducing the material's density. On the other hand, high-density polyethylene, used to manufacture bottles, drums, and pipes, has an average molecular mass in the range of 1 million unified atomic mass units. This form has less branching and, consequently, a higher degree of crystallinity. More generally, the properties of polyethylene can be tuned by varying the average chain length, crystallinity, and degree of branching, making it a highly versatile material. The physical properties of polymeric materials can be extensively modified by adding substances with lower molecular mass, known as plasticizers. These are typically low molecular weight esters of phthalic acid, which dissolve in the polymer, reducing the interactions between polymer chains. This, in turn, makes the material more pliable. Polyvinyl chloride, for example, is a hard, rigid polymer with a high molecular mass, commonly used in manufacturing drain pipes. However, when blended with a suitable plasticizer, it forms a flexible material used to make rain boots and doll parts. In some applications, plasticizers may gradually evaporate from the polymer, causing the material to lose flexibility over time. As this happens, the plastic becomes brittle and prone to cracking. Polymers can be made stiffer by introducing chemical bonds between the polymer chains, as illustrated here in red. This process, known as cross-linking, increases the rigidity of the material. The greater the number of cross-links, the more rigid the polymer becomes. Whereas thermoplastic materials consist of independent polymer chains, thermosetting materials undergo cross-linking when heated, allowing them to retain their shape. An important example of cross-linking is the vulcanization of natural rubber, a process discovered by Charles Goodyear in 1839. Natural rubber is derived from the liquid resin of the inner bark of the rubber tree. Chemically, it is a terpene, a polymer of isoprene, which is schematically presented here. Isoprene contains two double bonds, and polymerization typically proceeds at the two ends of the molecule, leaving a double bond in every isoprene subunit of the resulting polymer. During vulcanization, a controlled number of sulfur crosslinks are introduced by reacting the remaining carbon-carbon double bonds of adjacent chains with elemental sulfur in the presence of an accelerator and an activator compound. Vulcanization hardens the rubber and reduces its susceptibility to oxidation and other chemical transformations typical of olefins. Cross-linking approximately 5% of the double bonds creates a flexible, resilient rubber. When the rubber is stretched, the cross-links help prevent the polymer chains from slipping, allowing the material to retain its elasticity. I hope you noticed that nature also utilizes sulfide cross-links to rigidify and preserve certain protein structures, such as insulin, which you encountered in the lecture on proteins. In biological systems, the amino acid cysteine forms cross-links between peptides and proteins, contributing to their structural stability. To sum up, in this lecture, you have learned that plastics are materials that can be molded into various shapes, usually by applying heat and pressure. Thermoplastics can be reshaped, often by heating, whereas thermosetting plastics undergo an irreversible chemical process and cannot be reshaped. Polymers are largely amorphous, but some materials exhibit a degree of crystallinity. For example, high-density polyethylene, which has minimal side chain branching and a high molecular mass, possesses a higher degree of crystallinity than low-density polyethylene, which has a lower molecular mass and a greater degree of branching. You also learned that polymer properties are strongly influenced by cross-linking, where short chains of atoms connect the long polymer chains. For instance, rubber is cross-linked by short chains of sulfur atoms in a process called vulcanization. On the other hand, if we want to make a polymer more flexible, we can add low molecular weight molecules called plasticizers, which dissolve in the polymer and reduce interactions between polymer chains. In the concluding lecture of this module, you will learn about synthetic polymers produced through the condensation polymerization approach. Thank you for your attention. Hello, everyone, and a warm welcome to the concluding lecture in our series on synthetic and biological macromolecules. Polymers are an integral part of modern life. You already know that they are very large molecules constructed from a few small molecules that repeat many times. Earlier, we discussed one of the major classes of commercially important polymers and their formation through addition polymerization. Another general reaction used to synthesize commercially important polymers is condensation polymerization, also known as step growth polymerization. This type of polymerization typically employs difunctional monomers, with each new bond being formed in a separate step. Polymers produced via condensation polymerization have incredibly diverse applications, ranging from soft drink bottles to life-saving heart valve components. For instance, a St. Jude valve uses the polyester Dacron to attach it to the surrounding heart tissue. Dacron is DuPont's trade name for the fiber made from polyethylene terephthalate, which is a polyester. Approximately 250,000 valve replacement procedures are performed annually worldwide, most using St. Jude valves. The valve is secured to the surrounding tissue via a biocompatible polyester sewing ring. This polymer contains many polar oxygen-containing functional groups, which enable strong interactions with heart muscles and facilitate tissue growth. In this lecture, we will primarily focus on two types of condensation polymers, polyesters and polyamides. Our goal is to recognize the components of a condensation polymer simply by examining its structure. The monomers of condensation polymers must have two functional groups. We can represent such a monomer as shown here, where A and B denote functional groups that may or may not be the same, while R represents the remainder of the molecule. Most commonly, monomers link when group A on one molecule undergoes a dehydration condensation reaction with group B on another. You have encountered reactions like this when we discuss the chemistry of amino acids and the formation of proteins. Many condensation polymers are copolymers, consisting of two or more different repeating units. Two major types of condensation polymers are polyesters and polyamides. Polyesters are typically formed by the reaction of a diacid, or a derivative of a diacid, with a diol, an alcohol possessing two hydroxyl groups. Polyethylene terephthalate, commonly known as Dacron, is the most widely used polyester copolymer today, and you saw an example of its application earlier. Polyamides are formed by the polycondensation of a diamine with a diacid or a derivative of a diacid. The best-known polyamide is nylon 6,6, discovered by Wallace Carruthers and his associates at DuPont in 1934. It is named 6,6 because it is synthesized from adipic acid and 1,6-hexane diamine, both of which contain 6 carbon chains. Nylons are widely used in home furnishings, apparel, carpets, fishing lines, and toothbrush bristles, among other applications. Another well-known polyamide is nylon 6, also called Perlon. It is made from the cyclic amide caprolactam and is primarily used in ropes and ties. When caprolactam is heated with a small amount of water, some of it is hydrolyzed to the corresponding amino acid. Continued heating of this mixture leads to condensation and polymerization, yielding molten nylon 6. Note that we use a single-digit notation here because nylon 6 is a polymer composed of only one monomer, which contains 6 carbon atoms. If we represent the monomer of nylon 6 as A, the corresponding polymer can be depicted as a sequence of repeating A units, since all repeating units in the polymer are identical. Nylon 6,6, on the other hand, is a polymer composed of two different monomers. If we symbolize these monomers as A and B, the resulting copolymer can be represented as a sequence of alternating A and B units, as shown below. Polymers such as nylon and polyester can also be formed into fibers that, like hair, are very long relative to their cross-sectional area and are not elastic. These fibers can be woven into fabrics or cords and used to make clothing and other useful objects. For instance, nylon fibers undergo cold drawing, meaning they are stretched at room temperature. As the fibers are drawn, hydrogen bonds form between individual polymer strands. Specifically, the carbonyl group of one amide bond forms a hydrogen bond with the amide hydrogen atom of another strand, as shown in this figure. The tensile strength and stiffness of nylons are primarily due to this hydrogen bonding. Various substances can also be added to polymers to protect them from sunlight or oxidative degradation. For example, trace amounts of manganese and copper salts are added to nylons to prevent light-induced and oxidative damage, while also helping to maintain their whiteness. A short walk in most cities is enough to see that plastics are not easily degraded biologically. As a result, It is becoming increasingly important to design plastics with built-in susceptibility to bacteria or fungi. Natural polymers based on proteins and polysaccharides have this advantage. And so one approach to creating a synthetic biodegradable polymer is to use natural monomers to produce a polymer that closely resembles natural materials. Polyhydroxybutyrate is an example of a biodegradable polymer. It is even found in some microorganisms as massive whitish granules, occupying up to 80% of the cell's dry weight. It appears to serve as a storage compound for excess carbohydrates. A copolymer of 3-hydroxybutyric acid and 3-hydroxyvaleric acid is also found in microorganisms and is performing the same function. This polyester forms the basis of a strong, yet flexible plastic used in containers such as toiletries and is marketed under the name biopol. Since microorganisms naturally use polyhydroxybutyrate and biopol for energy storage, they can also degrade them. Biopol and other biodegradable polymers are manufactured by fermentation. However, they can also be synthesized chemically via the polymerization of a four-membered lactone called beta-butyrolactone. The polymerization is initiated by a water molecule that opens the first lactone ring. The reaction is then catalyzed by aluminum complexes and continues through repeated esterification of the exposed terminal hydroxyl group. Biodegradable polymers have found many applications in modern medicine. For instance, until the 1980s, patients who received stitches for a wound had to return later to have them removed. However, in the 1980s, biodegradable stitches were introduced. Once applied to the tissue, these stitches slowly dissolve without releasing any harmful byproducts. Today, biodegradable stitches are made from lactic acid glycolic acid copolymers that gradually hydrolyze over time. Modern synthetic materials, such as polymers, are increasingly used in medical and biological applications. For our discussion, a biomaterial is any material with a biomedical application. It may serve a therapeutic purpose, such as in the treatment of injuries or diseases, or a diagnostic purpose, such as in disease identification or monitoring physiological parameters like blood glucose levels. Whether its use is therapeutic or diagnostic, a biomaterial comes into contact with biological fluids and must possess properties suited to its application. For instance, a polymer used for disposable contact lenses must be soft and easily wettable, whereas a polymer used for dental fillings must be hard and wear-resistant. The most important factors influencing the choice of a biomaterial are biocompatibility, physical properties, and chemical properties, as illustrated in the right bottom corner of the screen. Specialized polymers have been developed for various biomedical applications. The extent to which the body accepts or rejects a foreign polymer depends on the nature of the functional groups along the polymer chain and their potential interactions with the body's own molecules, such as proteins, polysaccharides, and polynucleotides. Biopolymers in the body have complex structures with polar groups along their chains. Proteins, for example, are long chains of amino acids linked through condensation polymerization. In humans, 20 different amino acids combine in various sequences to form proteins. In contrast, synthetic polymers are generally simpler, consisting of either a single repeating unit or, at most, two different repeating units. This structural difference is one reason why synthetic polymers are recognized by the body as foreign objects. Another factor is that synthetic polymers often lack polar groups along their chains, limiting their ability to interact with the body's aqueous environment. Polymers can be characterized by their physical properties. For instance, elastomers are used as biomaterials in flexible tubing, such as coverings for leads and implanted heart pacemakers. They are also found in catheters, which are tubes inserted into the body to administer drugs or drain fluids. Special thermoplastics, such as polyethylene and polyesters, are employed as membranes in blood dialysis machines and as replacements for blood vessels. Thermoset plastics, though used more sparingly, also serve important functions. Because they are hard, inflexible, and somewhat brittle, they are primarily used in dental devices and orthopedic applications, such as joint replacements. For example, if you have ever visited a dentist, you may have noticed that when filling a cavity, the dentist packs material into the cavity and then shines an ultraviolet lamp on it. The light initiates a photochemical reaction that forms a hard, highly cross-linked thermoset polymer. To sum up, in this lecture, you are introduced to condensation polymerization, which occurs when a small molecule is lost during the reaction between monomers forming the polymer. The two main types of condensation polymers are polyesters and polyamides. You saw that when a polymer is formed from two different monomers, it is called a copolymer. We also briefly discussed biodegradable polymers, which are typically made from the condensation of naturally occurring monomers. At the end, we had a short overview of biomaterials, which are biocompatible materials with biomedical applications. Biomaterials are commonly polymers with special properties tailored to their specific applications. In the concluding module of this course, you will learn about the chemical composition of contact lenses. Thank you for your attention and participation.